All right, so we're continuing with our optimization problems. So the first example says a farmer has 1,000 feet of fencing available. There is an existing fence that separates his land from his neighbor's. Using that fence and his 1,000 feet of fencing, he wants to create a maximum enclosed area for his animals. What should the dimensions of his enclosure be to maximize that area? All right. So we have to think about the fact that we actually already have some fencing here. So this might be his neighbor's fence. He's going to put his fence up against it. So his fence might go something like this. He's got 1,000 feet of fencing that he can use. Well, I'm going to call this X and this X. So if each of those are X and he has 1,000 total fencing that he can use, what's going to be this length right here then? Right, so this is going to be 1,000 minus 2X. So now we know the dimensions. It's X by 1,000 minus 2X. What should the dimensions of his enclosure be to maximize the area? So we're going to look at the area. Base times height. So in order to find it, I'm going to take the derivative. Actually, I'm going to simplify it first. We get 1,000x minus 2x squared. Take the derivative. You get 1,000 minus 4x. We want to know in our area formula, where is that slope 0? So we're going to set it equal to 0. We get 4x equals 1,000. X is 250. That's our critical number. We're now going to take the second derivative, and the second derivative is negative 4. So because that second derivative is negative, that means we're concave down and we have to have a maximum at the critical number. So that's going to have to result in a max. And so therefore we know that this is going to have to be 250. This is going to have to be 250. This is 1,000 minus 2 times 250. So what's this going to be? 500. So those are going to be the dimensions that are going to maximize this area. If we were also asked to find what is that maximum area, I could do this. I can just do 250 times 500 and 125,000. Square feet. But they really just asked for the dimensions. So the dimensions are 250 by 500. Guys, even if you don't know calculus, you could still check or even do this problem. You could kind of guess and check to find the answer. But you can also even put just this original function in there. Just want to remind you of this, what's happening. Here's my area formula. If I'm just on a regular screen, negative 10 to 10, I'm not going to see everything because look at what these dimensions are. And because that number is so large, I know I'm going to have to extend this window. So I'm going to have to go from like 0 to maybe 600. And then the y is going to be my actual area. And I can see how large I think that area is. So I got to make this area even larger than that. Here's what the function looks like. But you got to be pretty... You have to kind of have some idea of what the answer is to even get that shape. And now I can say second trace calculate. I want to find the maximum. So I have to go over to the left side. I have to go over to the right side. And so now it's going to tell me that if I use an x value of 250, that's going to be the area that's going to be the result. See, if I look at my table of values, this is telling me that if I make x each of these values, this is going to be what my area is. So do you see how somebody who didn't really even know calculus, like I could teach them still how to find out that maximum area just by looking at the y's. Where's the y the largest? But this is going to take a lot of time. Calculus gets the job done much faster. All right, looking at number 2. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So we're going to have a square base. I don't know what the height is. It might be a perfect cube or it might not be. But we do know that this base has to be a square. So this has to be x and this has to be x. But this height can be anything. In fact, the classroom we're sitting in, the floor is pretty close to being a perfect square. But the height of the walls is not the same as the floor, the width or the length of the floor. Okay, so visualize this as being our box, what we're sitting in. And it says that we want to have a surface area of 108 square inches. So I have to write out the surface area of this. So what's the area of the floor? X times x is x squared plus, what's this base going to have an area of? Base times height. xy, and this is going to be xy. So what would I add on here to find the total surface area? Think of the room we're in, guys. The front is x times y. The side wall is x times y. The back wall is x times y. So what is it going to be? Plus, is it 3 or 4? 4xy. Has to be 108. Why didn't I do another x squared for the top? Open top, okay? So we don't have any top to it. If we did have a top, we'd have to use a 2 there. All right, so here's one of our equations. Now, let's keep reading again. What dimensions will produce a box with maximum volume? So what I'm really trying to solve is I want to maximize the volume. What is the volume right here? Length times width times height. What is it? X squared y, right? But in order to take the derivative of this volume, I have to get rid of the y. How will I get rid of the y? What do I have to do here? Solve for y. So I'm going to have 4xy equals 108 minus x squared. To get y by itself, I'm going to divide by 4x. So I'm going to divide each of these terms by 4x. Dividing everything by 4x. So these are going to cancel. I get y. 108 divided by 4 is 27 over x minus, simplifying this, is x over 4. So there's what y is. So I'm going to substitute that back into my volume formula. So y is 27 over x minus x over 4. Distributing that out, I'm going to have 27x minus x cubed over 4. So I have my volume formula. If I felt like it was too difficult to take that derivative, which on your homework, number 16, it's pretty difficult to take the derivative of number 16. So remember, you can find a maximum on your calculator if necessary. But this one is not difficult to take the derivative of. So I'm just going to do it. 27 minus 1/4 times 3 is 3/4 x squared. What do I do after I take the derivative? Set it equal to 0. So 0 equals, take this over, solving this. Well, if I want to get x squared by itself, I'm going to multiply both sides by 4/3. 27 divided by 3 is 9, times 4 is 36. Take the square root. Plus or minus 6. But I can't have a negative for a length or a width, so I'm going to throw that out. So x has to be 6. All right, just to make sure that that's going to maximize our volume, I'm going to take the second derivative. The second derivative is going to be negative 3/4 times 2 is negative 6/4, which is negative 3/2 x. If I plug in 6, that gives me a negative. That means I'm concave down. That means I have a max. Good, that's what I wanted. So 6 is going to be this. 6 is going to be this. How do I find out the height, though? Plug it in for y, right? Plug in right here so I can find out what y is. So I'm going to have 27 divided by 6 minus 6 divided by 4. Get that answer? And that's going to be 3. So the dimensions are going to be 6 inches by 6 inches by 3 inches. Those are the dimensions. If they asked for the actual volume, we can find that quickly. Oops, times 3. 108. And it is not the case that those will always be the same. That's just kind of a coincidence on this problem. All right, makes sense? Okay, let's look at your homework real quick, what you're doing there. So you're going to be doing number 6. This is something that we've already done. The sum of the first and twice the second is 100. Product is a maximum. You should know how to do that. When you get to number 16, on a given day, the flow rate of cars per hour on a congested roadway is given, where V is the speed of the traffic in miles per hour. What speed will maximize the flow rate on the road? See, what we're trying to find here is what is the best speed limit to have to get the cars through, but to still have, safety. So that's what you're trying to find here. What is the velocity? Now, you can take that derivative and set it equal to 0 to find it, but I'm telling you, if you don't want to have to use the quotient rule, this is pretty difficult to take the derivative of. Remember the other way that I showed you that you can find a maximum on the calculator, and I encourage you to do that on this one. 17 is similar to one I've shown you. 18, same way. Make sure you notice that you're not going to put that fence up there twice. That's a divider. You don't need fence there twice, just once. 19, you're going to verify that each of the rectangular solids has a surface area of 150. I don't care that you find the surface area of these, and I don't care if you find the volume of them. I just want you to do part C. I want you to determine the dimensions of a rectangular solid with a square base that would have a maximum volume if the surface area is 150 square inches. So just doing part C there on number 19. Okay? Any questions? All right, so go ahead and get out your book and get started on that.